Let's talk about TCP and UDP. Alright folks, welcome back to the channel. Today we're diving into something super fundamental. It's something that makes your internet work every single second. We're talking about TCP and UDP. Now I know these sound like super nerdy acronyms. And well, they kind of are. But trust me, understanding them a little bit can really help you get why some internet stuff is fast and other stuff is super reliable. It's like knowing the difference between a race car and an armored truck. Both are useful, but for totally different jobs, you know? We're going to break it all down. So, what's the big deal with these protocols anyway? Think about all the things you do online. You send emails, you watch cat videos, or maybe tech reviews, hopefully. You play games against people across the globe. All this data, these emails, videos, game commands, they don't just magically appear. They have to travel across the internet. TCP and UDP are like the two main shipping companies the internet uses. They decide how your data packets get from your computer to where they need to go, and back again. It's a huge, complex system. Now you might be thinking, why are there two? Why not just one super protocol? That's a great question. And the answer is pretty simple. Different tasks need different approaches. Sometimes, you absolutely need every single piece of data to arrive perfectly. Other times, speed is way more important than getting every tiny bit. It's all about trade-offs. Imagine trying to send a super important, fragile antique vase. You'd want the most careful, insured shipping, right? But if you're just sending a quick, hey, running late text, speed is key. That's the core idea here. In this essay, we're going to explore these two internet heroes. We'll look at what TCP stands for, and what it does best. Then we'll do the same for UDP. We'll compare them side by side, like a tech showdown. And most importantly, we'll talk about when you'd want to use each one. By the end, you'll have a much better grip on this behind-the-scenes internet magic. So grab a drink, sit back, and let's get into it. So, let's kick things off with TCP. What does TCP even stand for? It stands for Transmission Control Protocol. The name itself gives you a pretty big clue about what it does. Transmission, that's about sending stuff. Control, that's about making sure it's done right, with rules and order. Think of TCP as that super meticulous, slightly obsessive postman. This postman doesn't just toss your mail onto the porch. Oh no. He rings the doorbell, waits for you to answer, and gets your signature. He wants proof you got the package. The main job of TCP is to provide a reliable, ordered, and error-checked delivery of a stream of data. That's a mouthful, I know. Let's break it down. Reliable means it tries its very best to make sure all your data gets there. No missing pieces if TCP can help it. If a piece of data gets lost on the internet highway, TCP will notice and send it again. It's like our postman noticing a page fell out of your letter, going back to find it and putting it back in. It really cares about completeness. Then there's ordered. This is super important. TCP makes sure that the data packets arrive in the correct sequence. Imagine you're downloading a picture. That picture is broken into many small pieces or packets to be sent over the internet. TCP ensures that when those pieces arrive, they can be put back together in the right order. So you see the picture correctly, not some jumbled mess. It's like getting a multi-volume book series and ensuring you get volume 1, then volume 2, not volume 5 first. And finally, error checked. TCP has ways to check if the data that arrived is the same data that was sent. It's like our postman checks if the package he delivered is damaged. If something looks corrupted or messed up during transit, TCP can request that part to be sent again. This dedication to getting it right is what makes TCP so robust. It's not the fastest because all this checking takes time. But when you need accuracy, TCP is your go-to guy. It's all about that dependable delivery service for your precious data. So, how does TCP actually pull off this amazing feat of reliable delivery? It's not magic, it's just clever engineering. One of the key things TCP does is establish a connection. This is why it's called a connection-oriented protocol. Before any data is actually sent, your computer and the server it's talking to have a little chat. They perform something called a three-way handshake. It's like your computer calls the server answers, and your computer says, "Okay, great, you're there. Now they're ready." This setup ensures both ends are ready to send and receive. Once this connection is established, the data starts flowing. But TCP doesn't just fire and forget. For every chunk of data sent, the receiving end sends back an acknowledgement. We call these ACKs. It's like saying, "Yep, got that piece, send the next one." If the sender doesn't get an ACK back in a reasonable time, it assumes that piece of data got lost. So what does it do? It sends it again. This retransmission is crucial for reliability. It's a bit like a careful conversation where you keep saying "got it," so the other person knows you're following along. TCP also handles something called flow control. This is super smart. It prevents the sender from overwhelming the receiver with too much data too quickly. Imagine trying to drink from a fire hose. Not pleasant, right? The receiver can tell the sender, "Hey, slow down a bit, I'm still processing this," or, "Okay, I'm ready for more, speed up." This dynamic adjustment helps maintain a smooth flow of data without dropping packets because the receiver is overloaded. It keeps things efficient and prevents data loss due to congestion on the receiver's end. And let's not forget about that ordering we talked about. TCP assigns a sequence number to each packet. This allows the receiver to reassemble the packets in the correct order, even if they arrive out of sync. The internet can be a messy place, packets can take different routes. But thanks to these sequence numbers, it's like having numbered pages in a book. Even if you drop them, you can easily put them back in order. All these mechanisms, the handshake, acknowledgements, retransmissions, flow control, and sequencing, work together to make TCP incredibly dependable. Alright, we've seen TCP, the careful and reliable one. Now let's meet its wilder, faster cousin, UDP. UDP stands for User Datagram Protocol. That name, datagram, kind of hints at its nature. It sends data in individual packets or datagrams. Unlike TCP, UDP is all about speed and simplicity. Think of UDP as that super-fast courier service. They don't ask for signatures, they don't call ahead, they just grab your package and zoom off as fast as possible. Their main goal is to get it there quickly, not necessarily perfectly. The primary function of UDP is to send messages with minimal protocol overhead. It's a connectionless protocol. This means there's no fancy three-way handshake, like with TCP. UDP doesn't establish a dedicated connection before sending data, it just starts flinging packets towards the destination. This lack of setup makes it much faster to get things going. If you need to send something small and quick, UDP is like, alright, here it goes, without any prior discussion or formalities. It's the fire and forget approach. Because UDP doesn't bother with acknowledgements, retransmissions, or sequencing, it's incredibly lightweight. There's very little extra information or header attached to each UDP packet compared to TCP. This means more of the data being sent is actual user data, not protocol fluff. This low overhead contributes significantly to its speed. It's like sending a postcard instead of a registered letter in a big envelope with lots of forms. The postcard is mostly message, very little packaging. That's UDP for you, lean and mean. So what does this all mean in practice? It means UDP is fast, really fast. But, and this is a big but, it's not reliable. UDP doesn't guarantee delivery. Packets can get lost. Packets can arrive out of order. Packets can even arrive duplicated, though that's less common. And UDP won't do anything about it. It just sends the data and hopes for the best. It's up to the application using UDP to handle any errors or missing data, if it even cares. You might be wondering, Linus, if UDP is so unreliable, why would anyone ever use it? That's a perfectly valid question. It seems a bit crazy to send your precious data out into the internet wilds with no guarantees. But here's the thing. Sometimes speed is so critical that you're willing to sacrifice a bit of that perfect reliability. Or sometimes the application itself has ways to deal with a little bit of data loss, or the nature of the data means a lost packet isn't the end of the world. It's all about the specific needs of what you're doing. Think about live video streaming or online gaming. In these scenarios, getting the most up-to-date information as quickly as possible is paramount. If you're watching a live sports game, you want to see the action as it happens. If a tiny piece of a video frame gets lost, it might cause a very brief glitch, maybe a pixelated block for a fraction of a second. That's usually better than the whole stream pausing and buffering for several seconds while TCP tries to retransmit that lost packet. The show must go on, and quickly. Similarly, in a fast-paced online game, your character's position, or whether you fired your weapon, needs to reach the server and other players instantly. If a packet detailing your exact position from a tenth of a second ago gets lost, it's often better for the game to just ignore it and use the next more current packet. Trying to retransmit old stale data with TCP would introduce lag, and as any gamer knows, lag is the ultimate enemy. UDP says, here's the latest, go go go, and the game tries to keep up. Another reason UDP is chosen is for applications where the overhead of TCP is just too much for small frequent messages. A classic example is DNS, the domain name system. When you type a website address like linuxtechtips.com into your browser, your computer sends a tiny query to a DNS server to get the IP address. This is a small request and a small reply. Using TCP for this would mean a handshake, then the query, then the reply, then closing the connection. That's a lot of work for something so small. UDP just fires off the query and gets the reply. Much quicker, much more efficient for these tiny transactions. Section 6, the big face-off: TCP's safety net versus UDP's speed boost. So we've met our two contenders, TCP, the careful, reliable one, and UDP, the fast, no-frills one. Let's put them head-to-head and really highlight their key differences. The biggest, most fundamental difference is reliability versus speed. TCP is all about reliability. It establishes a connection, acknowledges data, retransmits lost packets, and ensures everything arrives in order. This makes it slower because all these checks and balances take time and add overhead. It's like having a very thorough quality control process on an assembly line. UDP, on the other hand, throws most of that caution to the wind in favor of speed. It's connectionless, meaning no setup time. It doesn't acknowledge data, doesn't retransmit lost packets automatically, and doesn't guarantee order. This makes it incredibly fast and lightweight. It's like an express lane with no toll booths and no speed limits, but also no roadside assistance if you break down. If speed is your absolute top priority, and you can tolerate some data loss or out-of-order packets, UDP is your champ. It's a clear trade-off. Another key difference is how they handle data as a stream versus individual datagrams. TCP presents data to the application as a continuous stream of bytes, in order. The application doesn't have to worry about packet boundaries. It's like reading a continuous scroll. UDP deals with distinct messages or datagrams. Each packet sent is its own independent unit. The application receives these individual packets and has to process them as such. It's more like receiving a series of separate postcards, each one a distinct item. Then there's the header size. Remember, headers are the extra bits of information attached to your data for the protocol to do its job. TCP headers are larger, typically 20 bytes or more, because they need to carry information for sequence numbers, acknowledgement numbers, window sizes for flow control, and so on. UDP headers are tiny, just 8 bytes. This means with UDP, more of the bandwidth is used for your actual data, especially for small messages. It's another factor contributing to UDP's efficiency and speed, especially when sending lots of small pieces of info. Section 7. When you need TCP, getting the important stuff right. Now that we understand the core differences, let's talk about specific situations where you'd absolutely want to use TCP. When is its reliability and orderliness non-negotiable? Well, think about anything where every single bit of data must arrive correctly and in the right sequence. If even a tiny piece is missing or wrong, the whole thing could be useless or corrupted. These are the scenarios where TCP shines, even if it means things take a little bit longer. It's the digital equivalent of needing a certified document. A classic example is web browsing. When you visit a website, your browser is downloading HTML files, CSS style sheets, JavaScript code, and images. All these files need to be transferred completely and accurately. If parts of the HTML are missing, the page won't render correctly. If an image is corrupted, it won't display. TCP ensures that all these components arrive intact and in order, so the website looks and functions as intended. You wouldn't want half a web page or a garbled one, would you? TCP prevents that digital catastrophe. Email is another perfect candidate for TCP. When you send or receive an email, you expect the entire message to arrive, attachments included. Imagine if random words were missing from your important business email, or if half of your attached TPS report just vanished into the ether. That would be a disaster. TCP's reliable, ordered delivery ensures that the email you send is the exact email that's received from start to finish, including all those crucial attachments. It's the bedrock of dependable electronic mail communication. File transfer is also a domain where TCP is king. Whether you're downloading a software update, uploading your vacation photos to cloud storage, or transferring documents to a colleague, you need those files to be bit for bit identical to the original. Any corruption or missing data could render the file unusable. TCP's error checking and retransmission mechanisms ensure that files arrive complete and uncorrupted. It might take a few extra seconds or even minutes for huge files, but the integrity of the data is preserved. That's the TCP promise for your important files. Section 8, Go UDP Go, when fast is what you need. Alright, so TCP handles the serious must-be-perfect stuff. But what about UDP? When does its fast and loose approach actually make sense? Well, it's all about applications where speed trumps absolute, guaranteed reliability, or where the occasional lost packet isn't a deal-breaker. These are usually real-time applications where old data is worse than slightly imperfect data. If it's late, it's often useless. UDP is built for these now-or-never scenarios where responsiveness is the name of the game. Live video and audio streaming are prime examples. Think about watching a live Twitch stream, a YouTube live event, or having a video conference call. You want the video and audio to be as close to real-time as possible. If a packet or two gets dropped, you might see a tiny glitch, a momentary pixelation, or a fraction of a second of garbled audio. But the stream continues. If you use TCP, the stream would pause and buffer every time a packet was lost, waiting for retransmission. That would be far more annoying for a live experience. UDP keeps the flow going. Online gaming is another huge area for UDP. In fast-paced multiplayer games, first-person shooters, racing games, MOBAs, your actions and the actions of other players need to be communicated with minimal delay. If your game used TCP, every time a packet with your character's movement was lost, your game would lag or freeze while TCP sorted it out. By then, you're probably toast. UDP sends game state updates like position actions very quickly. If one gets lost, the game can often interpolate or just use the next update. It's all about that low latency. Voice over IP, VoIP services, like calls made over Discord, Skype, or other internet calling apps, also heavily rely on UDP. Similar to video streaming, a slight audio blip due to a lost packet is generally preferable to the entire call, pausing or having significant delays. The conversation needs to flow naturally. UDP allows for that rapid transmission of voice data. Some VoIP applications even have their own clever ways to handle minor packet loss at the application layer, making the experience smoother even with UDP's inherent unreliability. DNS lookups, as we mentioned earlier, also use UDP for quick, small queries. Section 9. So, TCP or UDP, picking your digital delivery hero. So, there you have it, folks. The tale of two protocols, TCP, the reliable, orderly but somewhat slower guardian of data, and UDP, the lightning-fast, no-frills but occasionally unreliable speedster. They both play absolutely critical roles in making the internet work the way it does. One isn't universally better than the other, they are just designed for different jobs. It's like asking whether a screwdriver is better than a hammer. It depends entirely on whether you're dealing with screws or nails. It's all about choosing the right tool for the task at hand. When you need to be absolutely sure that every single piece of data arrives correctly and in the right order, TCP is your hero. Think web browsing, HTTP, HTTPS, email, SMTP, IMAP, POP3, and file transfers, FTP, SFTP. For these applications, data integrity is paramount. A little extra time spent ensuring everything is perfect is a worthwhile trade-off. TCP's connection setup, acknowledgements, and retransmissions provide that peace of mind. It's the protocol for when you can't afford any mistakes in your digital communications. On the flip side, when speed is the most critical factor and you can tolerate a bit of data loss or out-of-order packets, UDP is the way to go. Think live streaming, online gaming, VoIP calls, and DNS lookups. In these scenarios, getting information there fast is more important than getting every single old bit perfectly. The real-time nature of these applications means that retransmitting lost data would often cause more problems, like lag or buffering, than the lost data itself. UDP gets it there quick, or not at all. Ultimately, the choice between TCP and UDP is made by the application developers, based on the specific needs of what they're trying to achieve. As end users, we don't usually pick TCP or UDP directly, but understanding the difference helps you appreciate why your video stream might glitch occasionally but your emails always arrive intact. It's all part of the amazing, complex dance of data that happens every time you go online. Hopefully this has shed some light on these unsung heroes of the internet. Thanks for tuning in, and I'll catch you in the next one.